let us take the example of preparation of deca-3-ine. From acetylene. Okay. Now this is deca-3-ine. A triple bond after third carbon. Now, acetylene is this, right? Then these are the acidic hydrogens. Now these are to be replaced by these two things, right? Let us start with acetylene with, say, sodium amide or sodamide. So this is called monosodium acetylide. Okay. Now let us add this portion by taking the CH3, CH2 taken 4 times, just taken a carbon out for convenience. Now this attacks the carbon. In fact, from the back side, we will be getting HC triple bond C, to which CH2, let me write CH2 taken 5 times, and then the CH. Okay, now on to the other area. This one has to be replaced by this portion. For that, let us again treat it with sodium amide. Then okay, Na plus, 1 second. C minus, this one. Now let us take this alkyl halide. Okay. Finally, this is what we get. Deck, sorry, this one is CH2 taken 5. Just a second. Now let us see why are alkynes less reactive than alkenes. Okay, this is very interesting. Now it's very clear that both the alkenes and alkynes undergo electrophilic addition reaction, right? Now then, why are alkynes with the two pi bonds are less reactive than alkenes? Let us see the reason. There are interesting reasons. First one is, see, in electrophilic addition reactions, addition is initiated by an electrophile, right? Let us add H minus here plus here. Then add. See, when an electrophile is added, we get this. Now, this is in fact a vinyl. Vinyl is this CH2 double bond CH dash, right? Vinyl carbocation is what we got. Vinyl carbocation with a positive charge just on the double bonded carbon is highly unstable because, say, this positive charge cannot delocalize. The carbocation cannot undergo rearrangement, so is less stable. Vinyl carbocation is less stable as there is no possibility of delocalization. This is in case of alkynes. And when you go for alkenes, see what happens. Now, let us add the same H plus. Yes. Now the carbocation formed is a 2-degree carbocation. In fact, an alkyl carbocation, which is anyway more stable when compared to the vinyl carbocation, right? So this is one of the reasons why alkynes are less reactive. You have to check what happens when something is added. If you are ending up with something which is more stable, then go for it. But if you are ending up with something which is less stable, of course, you don't afford to go for it, right? So that is the first reason. Now the second reason. See, when something is added across a triple bond, we get this particular cyclic halonium ion. This again is less stable when compared to this particular halonium ion, what we get when the same bromonium ion is added across a double bond. So with respect to cyclic halonium ions also, the one formed from alkenes is more stable than the one formed from alkynes. Right. Now the last one. Coming to the triple bonded carbon, we know that they are of sp type. And we also know that with sp hybridization having 50% s character, bonded electrons are tightly held. By the nucleus. They are not that ready for participating in bonding with others. They are tightly held by the nucleus. So, alkynes are less reactive. Whereas when you go for alkenes, where the hybridization of the carbon atoms is sp2, with 33.33% s character, the bonded pair or the bonded electrons are not that tightly held by the nucleus. As a result, they'll be very much ready in comparison to alkynes to participate in reaction. Therefore, they are more reactive. So these are the reasons why alkynes are more reactive, though being with two pi bonds, than alkynes which have just one pi bond. Okay. Now the regular properties. The addition of halogen. Acetylene on reaction with a bromine in CCl4 solution. Take one equivalent in the beginning. Addition follows anti-stereochemistry. Just like in alkenes. In the first, then go for one more equivalent of bromine in CCl4. You get two more. Now these two are added in anti-manner. So from here to here, if you want, you can straight away go for 2 equal. Okay. Then the next one is addition of HF, hydrogen halide. Let us consider something which is unsymmetric to understand the addition of HF. Add one equivalent. According to Markovnikov, we get this. Of course, they are added in anti-fashion. Then on further addition of another equivalent of HCl, we get this. Okay. This is according to Markovnikov. Okay. Markovnikov addition. Even with the hypohalous acid also, I mean with halogen in the presence of water. Addition of halogen in the presence of water. Nothing but HOX, hypohalous acid. Even in this case also it is Markovnikov addition. This is treated with say hypochlorous acid, OH minus Cl plus, one equivalent. Then we get CH3C here, OH gets added, then double bond CH, Cl. Add one more equivalent of HOCl in the same manner. And here also it can be shown this way, right? Then negative to positive, negative to positive. Even in this case also. Take it the same way. No. It has to be this way. Let me take it here. Negative and then positive. Same way as in the first step. Now, it's the regular one. So you'll get CH3C, then here of course Let me just write it in this way. CH3, C, OH, another OH. Then here it will be CHCl2. Yes. Now see, this is unstable. See, a carbon having two hydroxyl groups on the same atom. I mean, this carbon with two hydroxyl groups is highly unstable. So it immediately undergoes elimination of water. Water molecule is removed. H plus and then OH minus. See, we get CH3, then C, double bond O, CH, Cl. Okay. This is what we get on adding hypochlorous acid. Okay. This is again according to Markovnikov water molecule is eliminated. Now let us see the addition of water. Taking two different reagents. Very important. See, in this, the first one is mercurational hydration. Using dilute sulfuric acid along with a small amount of say 1% mercuric sulfate. Okay. In this case also it is Markovnikov addition. Again, look at this. When propine is passed through a solution containing dilute sulfuric acid with small amount of mercuric sulfate, water molecule gets added in Markovnikov manner. Let's see. Take it this way. Then CH3C, here it is OH, and then double bond, this will be CH2, right? Now this is enol, en, double bond plus ol, OH. Enol form is unstable, right? Now this enol undergoes tautomerization. See, a bigger arrow mark is shown from the enol to keto because enol is unstable, but from keto to enol a smaller one is shown. Let us see what happens. As and when this comes here, This will go here. Then this carbon gets a negative charge and this abstracts the H plus, right? Now CH3, C double bond O, then CH. So in the beginning we got vinyl alcohol, and now we got keto form, which is a stable. This is of course acetone. If you want to know the factors that influence ketoenol stability, that is in fact tautomerism and the factors, you can just check our video. So with dilute sulfuric acid and mercuric sulfate, it is the Markovnikov addition which is followed. Let's see the other type of adding water. The second one is of course hydroborational hydration. See, in general for hydroboration we go for BH3, say BH3, THF kind of things. But here we'll be using a specific reagent. Let me first tell you what that reagent is. Of course, used earlier also. The reagent employed here is dicyamyl borate. Hope you remember. Okay. What is dicyamyl borate? Okay, let me first write what the full form of this is. Di, secondary, iso, then amyl, finally borate. Right? Okay. Di, secondary, iso, amyl, borate. Okay. Now this is the structure. See this. Di. Now this is a secondary carbon, and this area is iso. Overall, it's pentyl. Pentyl is also known as amyl, and finally, it's borane. That's it. Now, in this case, see the addition is according to anti-Markovnikov fashion. Okay, let me give you an example. dicyamylborane followed by the same H2O2 OH minus. In fact, it is the addition of water according to anti-Markovnikov fashion. Okay. Now, let us see. See, when water molecule is added according to anti-Markovnikov fashion, it will be CH3CH double bond C, then OH, this. See, I've added hydrogen to this and OH to this. This is according to anti-Markovnikov, right? Now, this again is a kind of enol. Enol is unstable, so is tautomerized. See, on tautomerization, this, then this, finally. So that will give us CH3, then CH2, then C double bond O, H. So we get an aldehyde. Of course, is known as keto form. So mercurational hydration is used for the preparation of ketones, whereas hydroborational hydration is used for the preparation of aldehydes. Right? That's it.